The link for the materials, I'm also going to put in the chat. The link for that notebook is also where I just put it, but you have both of those links in the chat right now. Yeah, I think we're ready to get started whenever you're ready, Helen.
Cool. Okay, I will share the workshop screen. Okay, can everybody see it okay? Cool. Okay, so I think just to kind of give an overview of what today will look like. So I have a series of videos that kind of walk through each of the sections. So just to kind of keep it easy to understand for everyone, I'm going to play the video in full screen within the shared Zoom window, and you can follow along in your copy of the notebook yourself. Definitely encourage you to follow along with every step of the way. It's definitely meant to be interactive. So if you have any questions at any point, probably just wait till the video is done playing. We'll have some time to chat through some questions, or while the video is playing, and if you're running into an issue, feel free to send me a message in the Zoom chat and I can help along there. Is there any questions from anyone before we get started? Nope. Okay, cool. So I'm going to go ahead and start off with the introduction video, which is just kind of an introduction to machine learning. Let's get started. Hey everyone, my name is Helen Schmidt, and I'm a graduate student in the Social and Affective Neuroscience Lab here at Temple.
Yeah, I can't hear it anymore. Let me see. I'm going to double check that, playing it on YouTube, it works.
It started off, I was able to hear the first few seconds.
Just also make sure that I share with the audio. I'm going to try playing it again. Let me know if anyone can hear it. Machine learning is the process of teaching machines to learn information. These machines can be computers or entire computing systems, or they can be simpler, something like an algorithm or a model. Machine learning to date has been widely used in computer science, data science, and neuroscience, and researchers with a psychology background are beginning to adopt this approach for a more data-driven analysis. Machine learning involves training a machine to learn about information and make predictions or classifications based on that learning. It's a subset of artificial intelligence and has grown in popularity alongside the recent AI boom that we've seen in the last year or so, as of the time of recording this video. While artificial intelligence describes the general development of computers that can mimic cognitive function, machine learning is more specific, using algorithms and large amounts of data to make informed decisions for specific tasks. Machine learning has become a popular tool for researchers in psychology and neuroscience, thanks to huge increases in computing power and access to data sets with thousands or millions of observations. Psychologists have seen great success recently in applying machine learning methods to gather insights about human behavior and cognition. Machine learning models can not only reduce time, effort, and human error costs, but they can also be applied flexibly across projects and data sets, including behavioral, survey, and neuroimaging data. The goal of this workshop tutorial is to introduce a variety of machine learning methods that can be applied to psychological data. We will examine the differences between unsupervised and supervised machine learning models and talk about the context to which they're best applied. This tutorial will also touch on model evaluation and comparison, and unpack how to determine certain model parameters given your data. An important note here is that this tutorial is by no means meant to be an exhaustive list of machine learning approaches. Rather, it's meant to serve as some introductory examples and methods that can be employed specifically in the R programming language. If you're interested in more complex machine learning approaches, a majority of these are actually supported in Python using libraries like PyTorch, TensorFlow, and Keras. These are more commonly what you might see in a machine learning tutorial online, but I hope this R-focused workshop serves as a complement to these other methods. Like I said, this tutorial is intended to be an introduction to machine learning with R, but you should have some existing familiarity with scripting and with R specifically before starting this tutorial. To wrap up this introduction video, I'm going to briefly outline the format of this tutorial. We will start off by exploring an example dataset and getting familiar with its variables. Then we'll introduce supervised machine learning methods and highlight two examples, k-nearest neighbors and classification trees. After that, we'll introduce unsupervised machine learning methods and highlight two other examples, k-means clustering and principal components analysis. For each method we introduce, there will be an interactive question for you to try out for yourself. Okay. Slide down. All right, so that kind of covered the what is machine learning portion of the notebook. So now I'm going to move to section 2, which is exploring the data set. And then I think this also, if I'm remembering my videos correctly, I think this also includes the supervised outline. The dataset that you will be using throughout this tutorial comes from the Palmer Penguins R package. This dataset and the images that you see sprinkled throughout the tutorial were created by Allison Horst and features data from penguins. This data was collected by researchers at the Palmer Long-Term Ecological Research Station in Antarctica. There are 3 different penguin species collected from 3 islands in the Palmer archipelago. What kind of data is included in this data set? If we look at the variables, we have species, which denotes the species name for each penguin. There's island, which denotes the name of the island that each penguin lived on. Bill length millimeters denotes the length of the penguin's bill in millimeters. And bill depth millimeters denotes the depth of the penguin's bill in millimeters. I've included an image to help clarify the difference between bill depth and bill length. The bill depth refers to the depth in millimeters of the penguin's bill if looking at its side profile. The bill length refers to the length in millimeters of the bill from the front of the bill to where it meets the head. In the variables, we also have flipper length, which refers to the length of the penguin's flipper in millimeters. And we have body mass, G, which refers to the mass of the penguin in grams. Finally, we have the penguin sex denoted as either male or female, and we have the year that the data was collected. Before we start with any machine learning, it's important to get a sense of the data you're working with. In the load data code chunk, we can load the data from the Palmer Penguins R package. Then we can examine the data using functions from the skimmer R package to show more information about our categorical and numeric variables. The next important step, for the sake of simplicity, is to remove any penguins with missing data. While you can run permutation tests to estimate missing data, here we will just remove the missing data. The final step in this code chunk is to get a correlation table of the numeric variables. This is helpful in determining what variables might be useful to examine in the context of a machine learning model. For example, flipper length and body mass are highly correlated. This makes sense, since the bigger the flippers are, the heavier the penguin is likely to be. Okay, now that we've loaded the data and examined it a little bit, let's create some visualizations. The first plot you'll make is the frequency of body masses across penguin species. You can see that Gentoo penguins tend to be heavier than Adelie and chinstrap penguins. Next, you'll make a plot that compares bill length to bill depth across penguin species. While these two variables are slightly negatively correlated when collapsing across species, we can see here that they're actually slightly positively correlated within each species. Let's also plot body mass compared to flipper length. Similar to the body mass distribution frequency plot we just made, you can see a clear separation of the data for Gen 2 penguins in particular. Finally, and this is just a fun plot to make, let's combine all of these variables and see how they compare across species. You can do this by creating a radar plot. This gives us a sense of how each of these species compare to each other on these 4 numerical variables. Okay, so now that we've examined and visualized the data we're working with, let's outline how we can use machine learning to analyze this data. In the context of psychology, a common area of investigation is determining differences between individuals. We often care about what makes an intervention or a cognitive strategy more effective for some individuals versus others. Machine learning can be particularly useful when we want to group data or compare groups, because we can reveal underlying structures or similarities that may not be apparent to human raters. In the Palmer penguins dataset, we can use the 4 data points for each penguin, including bill length, bill depth, flipper length, and body mass, as well as their species grouping, Gen 2, Adelie, and chinstrap, to develop a model that can be applied to new data. This would be a supervised machine learning approach. We can also see how well a model can classify penguin data into species groups when we don't tell the model in advance the species groupings, using an unsupervised machine learning approach. Okay, so that kind of covered the first exploration of the data set. So now we're going to move to section 3, which is the supervised machine learning approaches. This video will walk through both methods, and then there will be a chance to work through both of the examples after the video plays, so we can kind of end the video when it ends, and then take some time to go through the examples and ask and answer any questions.
Does anyone have any questions? If anyone has any issues or is running into any problems with the code, let us know. Make sure you're trying to run these chunks along with the videos as we go to make sure everything works and loads in correctly. And like Helen said, we'll try and avoid interrupting during the videos. This is a good time to chime in if you're having trouble.
I will go ahead and get started on this one. Supervised machine learning is a technique for data that contains labeled examples, such that each data point contains a number of features and an associated label. The goal of supervised learning is to map these features to labels based on example data and apply that mapping to classify new data. In the case of the Palmer penguins dataset, our features include bill length, bill depth, flipper length, and body mass, and our labels are the penguin species names. The first supervised approach we will discuss is a technique called k-nearest neighbors. This technique classifies data into specified classes. In this example, we will use the k-nearest neighbors algorithm to try to classify our penguin species based on just 2 of these data features, bill length and bill depth. The first thing we need to do is split our data into a training set and a testing set. In machine learning, it's pretty standard to use 80% of your data for training and 20% for testing. It's also standard to normalize your predictors, in this case, bill length and bill depth, to ensure that the scales of the 2 variables are the same. Okay, let's start in the KNN setup code chunk. Step number 1 is to set a seed to ensure that we get the same results every time. Because we will randomly sample our training and testing sets from the data, we want to make sure that we select the same rows for training and testing every time we run this script. We can set a seed using the set.seed function. Next, you'll want to generate a random set of numbers that accounts for 80% of the total number of rows in your data set. This will serve as your training set. I've created a function to normalize the predictors, but you can also use the native scale function in R. Using this normalization function, I will create a new data frame called df.norm and normalize the 2 predictors I'm interested in. I'll check that this normalization worked using the summary function. If it has, my variables should both range from 0 to 1, which they do. Now let's move on to the KNN model code chunk. Using the random set of numbers, let's split the data into a training and testing set. You also want to extract the species name to be used as the classification argument in the k-nearest neighbors model. Now that we have everything we need to run our k-nearest neighbors model, let's actually run it. Using the knn function, we can set the training set to df.train, the testing set to df.test, and the classification argument to df.category. We also can set our k to be equal to 3, which means that a testing point used by the algorithm will classify based on the 3 closest neighbors to that point. We can then show the accuracy of the classifier by calculating the proportion of penguins that correctly had their species classified. Sadly, our classifier wasn't particularly accurate at only 39.1% accuracy. However, this is above chance at 33%, so the algorithm is able to classify with some degree of accuracy. Let's try running the knn model again with a greater number of neighbors, like 10. Interestingly, that reduced our accuracy to 38.35%. This is still above chance, but shows that increasing the number of neighbors isn't necessarily the way to get a better classification accuracy. Okay, now it's time for you to try an example. In example number 1, use the knn algorithm to classify penguin species based on flipper length and body mass. Try a range of neighbors when employing the model to see if classification accuracy changes. In example number 2, use the knn algorithm to classify penguin species using all 4 data features. Again, try a range of neighbors when employing the model to see if classification accuracy changes. Feel free to pause the video here while you try your examples. Just to get a sense from the crowd, would it be helpful to pause here and try these 2 examples now, or wait and do the second examples and do all 3 examples together? Anyone have any thoughts?
It might be helpful to pause. I don't know if anyone's having the same issue, but I'm getting all NAs for the test data set, so I haven't been able to even run anything on it.
Yeah. Cool. I will close this then. So Katie, what's the section you're getting all NAs in?
For when you're setting the seed and like setting up the actual sample data set.
In the DF norm or the training and testing sets?
For the very first one under k-nearest neighbors.
Okay.
The DF norm, yeah, sorry.
Like line
it was like the first
187? Oh, sorry.
Yeah, the one you're on right now. And like the first time it like did work mostly, but there were some NAs, and so I couldn't get it to run the next step, so I went back and reran it, and now it's all NAs.
Okay. Did you run in the initial data set chunks? Did you run the section to like remove missing data and everything?
Yeah, I thought I did. I can redo it to see if that helps. Maybe I missed something, but I thought I'd gotten to the point where I ran everything up to the plots. So let me rerun those chunks and see if that helps.
Okay.
But at least we'll reset it so I can redo it.
Kim, based on your comment in the chat, I think that's probably just due to like a different sampling of like the testing and training sets.
Okay. That's what I figured. It's still pretty similar.
Yeah, it should be pretty similar. It probably is not going to be exactly the same as what I got, which I should have mentioned. But yeah.
Okay, doing that did help. And I don't have any NAs this time, so.
Okay, cool.
Is everyone else having success running the chunks and doing the bits of code?
I had success running the chunks, but maybe I just got lost, but I'm not sure like what to do, like how to get started for the example that starts with number 2.
Yeah. So the second example here.
I guess it says Oh, okay, yeah. Maybe it's because I'm looking at the wrong space too, but use the algorithm to. Okay, let me look at it for a second.
Okay, no problem.
Now that I know I was in the wrong spot.
As a rule, there are no dumb questions. So I ask all the dumb questions. So please feel free to also ask dumb questions. And I guess at some point, if anyone wants to volunteer to put their like test code in the comments, you can do that. I think it'll probably be easier than saying it out loud. Or we could do it out loud if that's something someone wants to do. But I know it might take a little bit, but I thought I'd put that out there. So if you finished code and it works and you want to pop it in the chat, you're welcome to.
Nice. It looks great, Kim.
I like when R gives me the different colors.
Yeah. Um, Giovanna, did you do the same that I had said to Katie, where you removed the missing values in the data set before reaching this chunk? Kind of like running all of the preceding code chunks?
Um, you mean like all the way up, um, in which section?
All the way back in under the Explore data section, there's
Yeah,
just a line that's removing penguins with missing data.
yeah, I did that. And before, actually, in my summary, I was getting NAs. And now, as you can see, like I'm not getting NAs, but I'm still getting no missing values allowed.
Yeah. What happens if you just kind of run all of the chunks again? It seems like maybe there's some issue with if like something was missing that maybe you forgot, or just like kind of resetting everything might fix it.
Yeah, I'll try.
Because it definitely shouldn't be saying you have missing data if you are not missing data.
For this second question, are we including sex and stuff like that, or is it just the uh length and depth and stuff for the.
Yeah, just the length and depth, like all of the like flipper, bill length, bill depth, and body mass. But you can also include the other ones and just like see how much better it gets.
Yeah, and I was
Just
wondering
for the
because I
sake
didn't
of
know.
simplicity, I've been doing those 4.
I didn't know if you could do categorical variables with this type of analysis, so I didn't want to pop those in there and
Yeah,
right.
I'm actually not sure if you can or not. So that would certainly be a good thing to try. I've only done it with numeric data. I think we'll do like a minute or 2 more on these before moving on to the next section.
Yeah, I was just about to send a message. It looks like it doesn't work with categorical data. You need like a meaningful minimum is what it says.
Yeah, that makes sense. All right, so I'm gonna go ahead and just reveal the code chunk answers for both of these. So Kim was like right on it with this one. Just basically the only change is adding which sections of the data frame that you want for this new classification algorithm, and then just repeating the same steps of separating out a training and testing set and running the same KNN algorithm. And then for the second example, again, just more variables within the data frame that you're normalizing and separating into your testing and training sets. Any questions from anyone on any of those sections or examples? All right, so I will go back up and continue playing the video for the second part of the supervised learning section. Okay, now that you've had a chance to try the k-nearest neighbors classification, let's move on to another supervised learning technique. This technique is called classification or decision trees. This is a technique used to draw conclusions, my apologies, about a set of data observations. Classification trees specifically are models where the target variable, in our case, the species variable, can take on a set of discrete values like Chinstrap, Adderley, and Gentoo. We can train a decision tree model using a selection of our data and then apply it to a set of test data, like we did with k-nearest neighbors. Finally, we can examine how accurately the decision tree was able to classify our penguins into their correct species category. Let's begin with the classification tree's code chunk in the tutorial. Because we're taking a training and testing set from our data, we need to set a seed to ensure the same results every time. This time, we'll create a function to split our data into training and testing sets for us. We will use 80% of the data to train the model and 20% to test the model. Now we can fit our decision tree model using the rpart function. We want to specify species in the model formula because that's how we're trying to classify the individual penguins. We also want to specify the method as class because the species outcome can only take on 3 possible discrete values. We can now run the model using our training data set. Once we run the model, the rpart.plot function creates a really helpful decision tree plot. When we previously investigated the data, we saw that Adelie penguins had the shortest flippers. The model identified flipper length as a way to distinguish between Adelie penguins and the other penguin species. If we move on to looking at the next level of the tree, once the model classifies using flipper length data, we see that it further distinguishes between Adelie and chinstrap penguins based on bill length, and between Gen 2 and chinstrap penguins using the island that the penguin was found on. Because we used the entire data set here, the model had the option of using information from the island, sex, and year variables as part of its classification process. So we might expect that the accuracy of this model with more data information might be more accurate than our KNN model. Let's find out using our test data set. We can use the predict function on the test data set along with our model and get a table of the penguins that the model could correctly classify. And this model did indeed do pretty well. It correctly predicted 26 Adelie penguins, but incorrectly classified 2 chinstrap penguins as Adelie penguins. If we measure the overall performance of the model, we see that it classified penguins at a staggering 95.52% accuracy, which is well above our KNN model's performance. But again, this kind of makes sense because we're using a lot more data to train the model. Now it's your turn to try a classification tree for yourself. Since island name and flipper length were important factors for the first model to classify the penguins, what happens to the decision tree if you remove island name and flipper length from the data frame and only classify based on the remaining data? Does it change the model accuracy? What does that tell you about the removed data? Give that example a try, and then join me after the break to discuss unsupervised machine learning models. Okay. All right, so everyone can take a few minutes and try the classification tree example for yourself. Let me know if you have any questions in the comments or sorry, in the chat or just by speaking, but otherwise enjoy. Yeah, I don't know why that would be different, Kim. It like really shouldn't be. I'm not sure if there was like something in actually like creating that function that somehow made a difference, but I don't know.
Yeah. I did double check the function against what's on the notebook. And it looks the exact same. So I don't know why it would be different.
Yeah.
And then I'm assuming this is because of differences in sampling, but then my decision tree looks a little bit different than yours.
Yeah, again, there will be slight differences just because of the sampling.
Okay.
But generally it should have similar percentages.
I have a question.
Yeah, go for it.
Can you maybe explain the classification tree output, like what each thing means, and how would you maybe use that in psychology?
Yeah, definitely. So you're talking about like the tree output here? Yeah, so basically the output, I think the most valuable information from it is the information that's at each of these lines, which is basically saying to you as like the viewer what portions of the data the classification tree is using to group penguins into. So the very top of the tree, so depending on the data, depending on the sampling, your tree may look a little different. It may have a different number of levels within it. If your data is really complicated, like psychology data often is, it will probably have like maybe 4 or 5 different levels that it's using to group data, but this is a relatively simple data set, so there's only 2 levels. So in this first line here, what it's saying is basically it's classifying Adelie versus Gen 2 penguins based on flipper length. So if a penguin has a flipper length that's less than 206 millimeters, it has a pretty high accuracy of 100% in like the confidence of the model in classifying that penguin as an Adelie penguin versus a Gen 2 penguin. So if a penguin's put in the within like the whole testing set, or sorry, the whole training set that it has, 62% of the penguins that it puts in are classified as Adelie based on the flipper length, and 38% are classified as Gen 2 based on the flipper length. Then you can go to the next level of the model saying, okay, of those 62% of the penguins, if the bill length is less than 43 millimeters, that would be an Adelie penguin versus a chinstrap penguin. So this is like a further breakdown of the percent of penguins that would fall into that category. As for the middle number, I actually don't know what that middle number is.
Yeah, that's what I was
to.
wondering.
Yeah. From like my own learning of these classification trees, everything I was reading was like based on the like category name and the percentages was how it was kind of easy to read the tree. So I would have to do more digging on that for you.
So this might be useful if you want to classify your subjects into groups, maybe.
Yeah, and because this is a supervised approach, you kind of need to have a sense of what your groupings could be in the first place. So say you had participants completing an experiment and there were 3 different conditions that people could be a part of, you would know that if it was not a double-blinded experiment, you might know who is in each category. So you could use that to kind of see how existing data where you know the category could then be applied to data where you may not know the category to see how well it can classify people into those conditions based on the behavioral data that you're feeding in.
All right, cool. Thank you.
Yeah.
Helen, I have a question about sample sizes of the data set.
Yeah.
To run like these kinds of supervised learning and also later unsupervised learning. Is there like a general rule for how large your sample size should be?
I don't think there's a general rule in the kind of research that I've done in terms of putting together this tutorial. It seems like as long as you have a few hundred observations, that seems to be good enough. Obviously, with more data and with more like values and like variables that you're putting into a model, the more accurately you can make predictions. But it doesn't seem like there's any sort of baseline standard. If there is one, I didn't come across it in like the other research I was doing, and it may just be something that people decide on their own.
I do know I took a machine learning class at one point in the computer science school, and they were like, you need to have like thousands of data points. Like there's no point in doing it. But I think that's like, you know how they say that with like fMRI, like I think it's one of those things where like, yes, at the core, like you should have as many as possible, but I think it's fine if you do it this way and you generally, just as long as you're aware of the potential implications, it's like, it's okay.
Yeah. No, I definitely agree with that. And even some of the other tutorials that I was looking at as like inspiration for this tutorial, people were using data sets of like 20 observations and making these same kind of models with that. And it seemed to be totally fine.
Yeah.
So I think it really is just a matter of understanding the implications, like you said, Katie. Oh, okay. I'm just seeing, Billy, your message in the chat too. If anyone else missed that as well about the correct example code for this example.
Yeah, that was my mistake. Katie had pointed that out. I must have put the later PCA, it looks like a little earlier than was intended. But I'm looking through and I think the rest of them are all correct.
Mainly just wanted the code because I didn't want to have to subset the data myself. I was like, I'll try, I'll do the rest of it, but I didn't want to have to write the code for that.
Oh, yeah. All right. Anyone want to share their code for the decision tree example in the chat?
Is anyone trying it and having problems? Is anyone stuck any particular place? I know it can be hard if you're not too familiar with R to go this fast, but we'll slow down if people need us to slow down, etc.
Yeah, definitely. If I need to slow down, like, please let me know. I'm very happy to take it a lot slower.
Oh, so Gigi, that could be just because I'm noticing the cache key thing. You might need to restart your R. That's a recent bug that's popped up in the most recent version of R if you're up to date.
Okay, so maybe that's why nothing is working.
Yeah. I don't know
It's
why.
possible, yeah.
It seems to be spotty. It's affecting me too, and I can't do anything about it. I wind up just doing like what is it, like Control Start F11 or something like that. Just like restart your terminal, and then it just goes away and everything works. I don't know
Okay,
why.
let's see.
Yeah. So I'm currently affecting it. None of my packages in R are working, so I'm just following along on
If
this.
I should I like force our student and as well as R to quit?
Yeah, I'm trying to remember if it was there's a way to close it and like not lose your environment. I was it like function F11. Um
I have a Mac, so there's also that.
yeah. There's still should be, oh wait.
Yeah, every day when I walk through the days streets of Dunedin.
So yeah, I think for Macs it should be
My God,
command.
Dr. Newcomb's voice came from heaven. I'm sorry, that was my laptop.
No, you're good.
I
I
think
forgot I had like a video that like just started out of nowhere.
it's okay. I think on Macs it should be Command Shift F10. If you press that, then it will restart R without, I think, losing your environment, and it will hopefully fix that issue.
Oh yeah, I think it's working. Thank you.
Yeah, no
Let's-
problem. Hopefully, let me know if that doesn't, if you still get that error.
Yeah.
Oh, that's fun. You had such a different tree, Katie.
Was it like super different?
I mean, there's just more levels.
Okay, interesting.
Which is fun.
Yeah, it must have been like the different subset and how it was like laid out.
Yeah. I think the one that I made when I did the example still only had 2 levels, which was kind of sad because I was like, oh, I want it to look different.
Cool. Nice.
Cool. Awesome.
I also thought that for a moment, Gigi. I was like, what? What is Nora doing on a machine learning?
What is she talking about?
Nora's going for a late career attention shift. She's like, now's the time. I'm gonna become the next machine learning person.
All right, final call for anyone to share their code.
It's working out, Billy, though. Thank you.
Nice. All right. Guess we have no takers, so I'll just reveal the answer code. But it should look something like this, where you're just selecting only
Sorry,
the data that you want to work with. Sorry, were you gonna say something, Billy?
I was gonna say, I think this is the wrong one. Sorry, I put in the chat. I accidentally put
Oh.
this is the PCA.
Right.
I put a
I
link
saw
in the
that,
chat
and
for the
I'm
machine
now
learning
just
one.
ignoring it.
Yeah, my bad.
I think you put all the solutions in here
Yes,
too.
right. That's what the link is to. So if you just
Gotcha.
click, yep, you got it.
All right, I'll just
Yeah,
show
that was
this
my
one.
fault.
So yeah, so this should be generally what you do for just using the subset of data. So yeah, anyone have any questions on that or concerns or anything about supervised machine learning? Because that kind of ends the first section of the tutorial. All right. So I think now we have a short break scheduled. So feel free to get some water, stretch your legs, and we'll be back for unsupervised learning in like 5 minutes or so.
And if anybody does have any other questions that haven't been like put in the chat in terms of like setting anything up, having any coding issues, feel free to shout them out. I'm gonna be here during the thing. I'm gonna be here trying to get my R to work because it's killing me. That's not.
Oh no. I hope your GG plot gets fixed.
It's not even the GG plot. It's all of my packages are dead, and it's not letting me. It says my R lang is outdated, but it's not letting me update it. And
That was the
so
problem I was having.
like 9 of the packages that you're using, it will not let me do anything for it.
Oh no.
I went in and I updated the permissions on the back end because I thought maybe, I just didn't give myself like admin permission. That's not working. Like I just have no clue what this is.
I uninstalled and reinstalled an older version of R because I could not get it to. I could not find a solution.
Man.
Was this the problem you were having, Katie, when we were like editing this?
Yep.
Okay.
All right, I'm just gonna grab some water, then I'll be back.
Yeah.
Katie, did you mention you had to download an earlier version of R?
Yeah.
Okay. I don't know if this is the most recent version, but this is like from March 15th, 2023. And I've had this issue where I had to like spell out false instead of just doing F before.
Oh.
I don't
saw
know
that.
why.
I tried Googling it.
Yeah.
I didn't find anything on it.
So yeah, I have no idea. And I had to do the same thing whenever I like did the example code too. So maybe it's some weird thing with the most recent R version. I don't know.
Yeah. I think the version I went back to wasn't that far. It might still be like. I also, honestly, now that you say that, I was also having issues using just F. So I definitely was I was spelling out false, but I didn't know that that was like an issue. So that's good to know that was part of the problem.
Okay.
Was it, Kim, was it just for, sorry, I don't remember if it was it for like a specific package where that wasn't working? Do you know, or like?
I don't remember when
Was
the
it-
last time it didn't work for me.
Because I
Let
noticed
me,
in
I
the
can look
chat,
back
you
on my
said it was like
code.
oh, sorry, go ahead.
No, I was just saying, let me look back on like some other code and see where I would have used it.
Oh, was this like before, even before this tutorial you were
Yeah,
having?
it was before this
Oh.
workshop. Yeah.
Okay. I was gonna say I noticed the create train set thing gave you an issue, and I was gonna wonder if it was maybe just like bad code writing on the part of that package. But if it's like other packages, then it's, I don't know, it's probably just R.
But I mean, it sounds like it's working for everyone else without having to spell out false.
Yeah. Hmm.
I think it was when I was using ggplot
Hmm.
to make some like complicated plots. Because I think I have false spelled out for like some aesthetic things, like showing the legend or not showing the legend. But yeah, I don't know.
And it doesn't do the same thing for T, like T works, but F doesn't.
Yeah, T works,
Oh,
but F doesn't.
that's so weird. I found this like, I don't know if this is at all helpful. I found this like blog where somebody was talking about you could accidentally redefine T or F within your system or something.
Oh,
I don't know if, but I don't know like where, if it's like in your R history or something like that, where that would sit.
yeah.
Um,
I guess that, yeah, that makes sense if I would like define an object as the name capital F, but I
right,
don't
but you're not
have
like
that here.
explicitly doing it, so that's why I'm like, I don't know if it's
No,
actually that. The only thing I could think is
yeah.
like there's like some like R
Like a
history
package.
document or something like that that's like doing it. Yeah, maybe
Yeah.
package might make sense too. I don't know, the most recent iteration of R has like, I've seen a lot of people online complaining about a lot of bugs. And I don't know which one they're on. I don't know which version I have right now, but I'm having the same
Yeah.
problem that Gigi was having too. So yeah,
Okay.
it's tough. Um,
Thank you for sending this our bloggers post, Billy. I had no idea that using TNF was such a bad idea.
Yeah, I didn't realize. I mean, it makes sense. Like, I just never really thought about naming a variable as T or F and that you could redefine it, basically.
Yeah.
We were talking about maybe it's like in one of the packages I have installed, but internally they have defined like capital F as something. So it's
Oh,
not something that I'm explicitly naming an object capital F.
Right.
I don't think I've done that.
Just seems like I don't know. I feel like I can count the number of times I've ever named a variable like one letter on like one hand. Like I don't know. It feels like
yeah,
it can be a recipe for disaster.
definitely. Maybe we'll just wait another minute or two for people to come back from the break before we get started.
Hey, are you guys still doing coding office hours?
Not during the summer, but if you do have any questions, just like shoot us a message on the Slack and like we can just like
Yeah.
meet with folks as needed. But yeah, I think we'll pick those back up in the once the semester starts back up in the fall.
Okay, sounds good. Yeah, I thought about the Slack is great. So
Oh, okay,
let's
cool.
do that.
Yeah. Yeah, and like I said, we can always like pop on Zoom or whatever if it's like something that's a
Yeah.
little bit more involved.
Yeah, with the summer workshop series and the intro to coding boot camp, it's like we got to give ourselves
Yeah, no,
something
it's a lot.
to.
Yeah.
I did have several people ask that though, so I know I'm glad that people like find it useful and actually utilize it. Sometimes
Yeah.
it's like we're just sitting there alone, and it's like, does anyone like this?
Yeah, it's funny. It's like crazy. There'll be like days where it's just Katie and I for like 2 hours, and then like there's another day where there'll be like 5 people all
Yeah.
like vying for our attention.
Yeah.
Me, I was just thinking about it because sometimes I'll like try to do the workshops afterwards or try to do the ones that I missed, and then I'm like, this is not working.
Yes. Yeah. And I need to put up like a tutorial on how to open issues on GitHub, because you can, if that's something that you encounter, you should be able to like just say right on GitHub, like, oh, I'm having a problem with this. And then it'll go directly to
Oh,
us to be able to figure out. So, well, I should put
That's
up like a little blurb about that.
That is a great idea. Yeah.
Yeah.
yeah, I would like
Um,
to learn about that. I didn't know about it.
Helen, you
never-
want to start back up? Sorry.
Yeah, sure.
I don't want to keep people too long.
No, totally. Alrighty. Okay, so we're going to get started on the second section here, which is the unsupervised machine learning section. We can do the same thing that we did for the previous section, where I'll pause the video after we kind of introduce the first example, give some time to do the example, answer any questions, and then we'll wrap up with the final example. And then we can have some time for just like general Q&A or just like time to finish anything that you may have not gotten to with the pace that we've been going at. So I will go ahead and get started on the video. Unsupervised machine learning is a machine learning technique for data that does not contain associated labels or categories. There are two main goals to unsupervised learning: clustering and dimensionality reduction. In this section of the tutorial, we will introduce two techniques. The first is k-means clustering, which will help cluster the data into categories. And the second is called principal components analysis, which will help reduce dimensionality within the data. The first thing we need to do is remove the species label from our data set. In unsupervised machine learning, there are no labels provided alongside the data. Since we're working with a data set that already has labels, we can remove these labels and see how well unsupervised machine learning models perform. In our new data set, we will select only bill length, bill depth, flipper length, and body mass variables, and remove labels like penguin species, penguin sex, and island location. Let's start off with a technique called k-means clustering. This unsupervised technique assigns each data observation to one of k clusters based on the nearest cluster centroid. In this technique, we need to specify the number of clusters we might expect from the data. We can do this manually or iteratively to find the optimal number of clusters based on the data. I've included a series of visualizations in the tutorial that I find really helpful in visualizing the process of assigning data observations to these cluster centroids. In this example, we will use a k value of 3 as a hypothesized number of clusters if we want to classify species. We can also use a k value of 2 if we want to classify a number of clusters based on penguin sex. For simplicity, we will only use flipper length and bill length observations. K-means clustering can handle more than 2 dimensions of data, but in order to compare the classifications to the visualizations that we made using the full data set, we'll just use 2 dimensions for now. Let's start in the k-means clustering code chunk. For the new unlabeled data set, I just want to extract flipper length and bill length variables. We can create another plot to visualize how bill length compares to flipper length by species. Running k-means clustering is as simple as using the k-means function in the R-stats package. We have to set a seed, and then we can run the k-means function on our unlabeled data set that contains just flipper length and bill length. We can set the number of centers, or k value, to 3, since we know that there are 3 different species of penguin in this data set. I will also set the end start to 25. which tells the model to choose 25 random rows in the dataset as initial centers. Once we run the function, we can examine the structure of the resulting clusters and visualize them using the fviz_cluster function. If we eyeball the plot made with the actual species labels and the plot made from the k-means clustering, they generally are pretty similar. What if we try to cluster based on penguin sex, therefore using a k-value of 2 instead of 3? We can create a similar whole dataset visualization based on penguin sex and repeat the k-means clustering. As we can see, there's more overlap between the two groups of penguins based on sex, so the k-means clustering plot doesn't look as similar to the real data. But what about if we have data where we don't know the true number of groups, as we so often do with multidimensional behavioral or neuroimaging data? Well, we can determine the optimal number of clusters based on our data using a few different methods. This process can be somewhat subjective, but we can use 3 different methods together to attempt to reach a consensus about the optimal k-value. The first method is called the elbow method and aims to find a k that has the smallest within cluster sum of squares, or WSS. The total WSS measures how compact the clusters are. The elbow method examines the total WSS as a function of the number of clusters and aims to find an optimal number of clusters such that adding another cluster wouldn't improve the total WSS. We can use the fviz_nbclust function in the optimizing clusters WSS code chunk to run the elbow method on our unlabeled subset data. Based on the plot, it looks like the optimal number of clusters is 4, since the total WSS doesn't get much lower for 5 clusters compared to 4 clusters. Comparatively, there are notable jumps in the plot, down in total WSS from 1 to 2 clusters, 2 to 3 clusters, and even 3 to 4 clusters. We can also use a method called the average silhouette method, which measures the quality of a clustering. A high average silhouette width indicates good clustering. With this method, the optimal number for k is the number that maximizes the average silhouette over a range of possible values for k. We can use the fviz_nbclust function again in the optimizing clusters ASM code chunk and specify the silhouette method. Based on this plot, it looks like the optimal number is 2 because 2 clusters corresponds to the maximum average silhouette width. The final method we'll try is a statistical method called the gap statistic method. This method compares the data against a null hypothesis. The gap statistic compares the total within intra-cluster variation for different values of k, with their expected values under a null reference distribution of the data. The optimal number of clusters is a value that maximizes the gap statistic and means that the clustering structure is far from a random uniform distribution of observations. We can use a function called clustgap in the optimizing clusters gap statistic code chunk. This method also suggests that 4 is the optimal number of clusters. This is consistent with the 4 clusters recommended by the elbow method, but inconsistent with the number recommended by the silhouette method. There's not really a clear consensus here, but we can be relatively confident that using a k-value between 2 and 4 is likely optimal. And we can visualize how our data is classified based on these varying k-values. In the KMC code chunk, we first repeat the k-means clustering using a k-value of 2, 3, and 4. We can then plot these together to compare. Now, because we know that this data can be grouped into 3 known species, the recommended cluster of 4 doesn't actually make sense. But when we don't know the true category structure for the data, using these techniques to find an optimal number of clusters can be a critical step to identifying that underlying structure. Okay, now it's time for you to try k-means clustering for yourself. Using only the build depth and body mass variables, repeat the k-means clustering and the steps to find an optimal k. Does the number of optimal clusters change? Feel free to pause the video here while you try these examples yourself. Okay, I will pause the video here. and you can all try the example for yourself. It might take a few more minutes than the previous examples just because there are a lot of steps involved, but if you have any questions as you go, definitely let me know.
I'm curious if I'm getting a cluster of one. Obviously that's not helpful because that's just the data set itself. So do we, I like try that out just to see how it looks on the graph, or do you, not go and do one cluster?
Yeah, I think probably just for visualization's sake, it might be useful to just show one. I mean, it will just look like the
Yeah.
data, but if it's recommending one as a cluster, that's still like a little informative just because it's saying that like there's probably not a better way to group sections of data points. So that would still be useful to see.
I don't know if anyone else is having this issue, but if you have the mass package installed at the same time as dplyr, it doesn't know which select function to choose from whenever you're subsetting the data frame. So I had to define the dplyr select function.
That's a great call. Thanks, Kim.
Did you draw the whole those those cute centroids and stuff?
I did not. The same person who provided all of the penguin data also drew the k-means breakdown. So I will actually link the website with all the visualizations on it because there's a lot out there in case anyone wants to use them yourself.
It all looks very good.
And I'm wondering, so I'm running it successfully and it looks different than the previous example, but I'm still getting the same Y and X axis labels. I'm not sure why that would be because I thought that would come, I mean, I guess it's unlabeled, so.
Yeah.
And there wasn't any like point where you really defined that, at least for that one right there that you're on.
Yeah. So you're getting like, instead of bill depth, you're getting bill length.
Yeah.
But
it's like clearly like different data, like it looks different than this, like the graphs come out differently. So I don't think it's not the same data itself, I don't think.
Yeah, I'm just wondering, like, the only thing I could think of is if you're using like, if you didn't take a new subset of the data.
Oh, I didn't change that, so maybe that's what. It's so strange because it looks different.
Yeah.
I did take the new subset, but I didn't change that
Okay.
particular variable. So let me see if that helps. Okay, yeah, that worked. And it looks even more different, so that's fun.
Nice. All right, let's take like a minute or two more to just finish these out. And in the meantime, if anyone wants to share like a screenshot of their different plots that they made, that would be really fun to see. Oh, nice. That looks great, Katie.
So funny, I'm learning more in this than I ever did an entire class's worth of machine learning in the computer science department.
Nice.
I was never able to do this there, so this is great.
Cool.
Anyone else have an example they can share? We're interactive, folks. Let's go.
Sharing code or screenshots is totally fine.
Cool. Thank you, Allison.
Nice.
Nice.
Looking great.
Whoa, Kim, yours is cool. What's going on there?
Okay, cool. These are looking great. Anyone have any questions about k-means clustering before we move on to our final example? All right, so I will play the last part of the video for this one. Oh, very nice, Emily. Awesome. Okay, yeah, so I'll play the rest of the video and then we'll do the final example and we'll be close to being done. All right, let's introduce the final technique in this tutorial, an unsupervised approach called principal components analysis, or PCA. This is a technique that reduces dimensionality in a data set. In the Palmer penguins data, we have 4 data dimensions: bill length, bill depth, body mass, and flipper length. As we just discussed with the k-means clustering, it's difficult to visualize all 4 of these data dimensions together. Using PCA, we can transform the data into lower dimensional space and collapse highly correlated variables together. We can then extract important information and visualize the data more easily. The first step within the PCA code chunk is to normalize all 4 variables in the unlabeled data set. We can do this using the normalization function we created earlier on in the tutorial. Then we can compute and visualize a correlation matrix for all these variables to see which are highly correlated with each other. Like we saw during our data exploration, body mass and flipper length are highly correlated, so these may be good dimension reduction candidates. Next, we'll conduct our PCA using the prin-comp function in the stats-r package. We conduct the PCA using the correlation matrix in order to help the model identify these highly correlated variables. Using the summary function, we can see that the standard deviation, the proportion of variance in the data explained, and cumulative proportion of the variance explained for each newly created component. The number of components corresponds to the number of variables in the data set. The first component accounts for 95.8% of the variance, and the second component accounts for 3.85%. So together, they account for nearly 100% of the total variance in the data. But what do these components even mean? We can investigate that using the loadings of each component. Component 1 has positive values for bill length, flipper length, and body mass, but a negative value for bill depth. This implies that penguins in component 1 are heavier and have longer flippers and bills, but shorter bill depths. Component 2 has positive values for bill length and bill depth, but negative values for flipper length and body mass. This implies that penguins in component 2 are lighter and smaller, but have bigger bills. We can visualize the relative importance of each component using something called a scree plot, and which can be used to determine the number of components to retain. Clearly, we want to retain components 1 and 2 because they explain some variance. They explain a lot of variance together. We'll also examine the data using a biplot to see similarities and differences between the samples and show the impact of each attribute on each of the components. We can gather a few pieces of information from this plot. Variables that are grouped together are positively correlated to each other. The higher the distance between the variable and the origin, the better represented that value is. And finally, the variables that are negatively correlated are displayed on opposite sides of the biplot's origin. Okay, now it's time for you to try out PCA. Let's pretend that the penguin species variable is the only label variable. If you recode penguin sex as a numeric variable, where 0 is male and 1 is female, what is similar or different in the PCA analysis? All right, so everyone can go ahead and try the example for themselves. Take 5 or so minutes or so, and let me know if you have any questions. All right, we'll take another minute or two. If anyone wants to share any code as they work through it, definitely feel free to do so. Thanks for sharing, Katie.
This is a big throwback to Tom's class, so.
Yeah.
You didn't realize I was teaching machine learning, did you?
You're setting us up for success.
Or for the sarcastic comment of, I didn't realize that things that were developed in like the 60s and 70s were newfangled trendy toys.
Yep.
Just put a pretty ball on it and they won't notice.
All right. Anyone else have any code or questions that they want to share? If not, I will wrap up with just a short little conclusion video, and then anyone who wants to stick around, whether they want to continue working on the workshop or if they have additional questions, like feel free to do so. But this is pretty much the end of the workshop content. So just wanted to say thanks everyone for coming. This is really fun to put together, and I hope you all learned some fun stuff about machine learning. So I'll play the video and then I'll see some of you afterward, hopefully. I hope this tutorial has served as a useful introduction to machine learning methods in R. We discussed how to apply both supervised and unsupervised machine learning models to a publicly available data set. These techniques include k-nearest neighbors, decision trees, k-means clustering, and principal components analysis. By using these relatively simple tools in a programming language that's already popular among psychology and neuroscience researchers, we're able to make these techniques more easily accessible and applicable to a variety of data sets, research projects, and topics. This is by no means a comprehensive tutorial about machine learning, and if you're interested in learning more, I would highly recommend checking out some machine learning tutorials in the Python programming languages. There are libraries available like PyTorch, TensorFlow, and Keras that are designed to support powerful machine learning models. I hope this tutorial has served as a good introduction and that you feel empowered to continue learning more about these techniques. Cool. All right.
Yay. Thank you, Helen. That was really awesome. I definitely learned a lot. I hope everyone else did as well. Is there any questions, concerns, anything else for Helen before, yeah, Gigi?
Yeah, I have a question.
Yeah.
What are a few examples of when you use an unsupervised versus a supervised method?
Yeah, the biggest difference is whether or not you kind of know labels for your data already. So kind of in the example that I gave you earlier, when you have conditions that say participants are put into and you know the conditions they're put in, you're able to apply a supervised machine learning approach because you can tell whatever model you're putting together, like this is how the data should be categorized, and you can train a model on that categorized data and apply it to new data. If you didn't know any sort of structure that's underlying your data, say you were trying to figure out if a group of double-blinded groups of participants were, say they had more or less success with a given intervention, then you could apply an unsupervised learning technique, which would help you identify the structure of the data.
Yeah, so unsupervised is more like exploratory. It's like exploratory.
Yeah, it's more like data driven.
Right.
Yeah,
Okay.
you can use
Sorry,
it for like
sorry if this
exploratory.
was repetitive. I'm just
No,
not
no,
familiar.
no, you're so good.
Thank you.
Yeah, of course.
Helen,
Any other? Oh, sorry, go ahead.
sorry, Billy.
No, it's fine.
Have you seen any applications where folks have used an unsupervised approach where they included the known classifier as one of the indicators and compared that model to a model where you did supervised classification? Because there's a little bit of the sort of funky sleight of hand where in the supervised learning context, you know the outcome, but that outcome could also be an indicator that's used to develop the classification.
Right.
But I genuinely have no idea what that kind of manipulation would do to the utility and the clarity of the solutions. I don't know if you do.
Yeah, I don't know of anything off the top of my head specifically that people have done. But it sounds like something that I'm sure people have done. My sense from putting together this workshop is a lot of times these methods are used together for a given analysis. So someone might do a series of machine learning models as like different steps in their analysis pipeline. It's never, from my sense, at least that I've gotten, it's never just one model being used and kind of like the results being taken at face value. It's always kind of in combination with other things.
Yeah, I think that point is really important, Helen, where folks test a whole lot of models and pray to whatever kind of entity they wish to select on, that there's convergence.
Yeah.
And it's interesting when there is convergence, it's interesting when there's not convergence.
Definitely.
Really nice job, Helen.
Thanks, Tom.
Any other questions?
Oh,
Yeah.
You got
Me and
it.
Billy saying the same thing.
Yeah.
If there aren't any other questions, thank you everyone for attending this week. Just as a little preview for next week, Stephen Martinez will be presenting on JS Psych, which is kind of like an experiment builder in JavaScript. So that'll be another, I feel like we've had a lot more like intro to things so far this year, but I think it'll be really helpful for those building experiments on their own. And it's particularly good for if you want to host them on the web, which is become a lot more popular since COVID. So I know a lot of us in the department were having trouble integrating various like languages and hosting things online. So it seems like Stephen found a lot of success with this program, and he'll show us how to use it next week.
Yeah, if you're building experiments on CyclePy and hosting them on Pavlovia, it's just JavaScript. So
Yeah.
you know, it's really, really great to go right to the source if you can.
Cool. Otherwise, thank you everyone for attending. We appreciate it.
Oh, yeah.
Yeah, thanks everybody.
Thanks, guys.
Thanks, Helen.
Thanks, Lynn.